where if you were the expert, that you would reinforce. And also, when you do so, you can actually comment on the chat to say why you are actually specifying these areas. In the Desmos link, you can see that there is a diagram of one of the planes that have actually returned with some bullet damage. And there are some red areas on that diagram where you can actually see the bullet damage. So there are certain parts which have lots of red dots, and there are certain parts which don't have lots of red dots. So let's see what are your responses. So while we are seeing the responses, Mahfouz, since you are with us, what do you think? Does it make sense to reinforce any specific area?
Well, thank you. The plane, from the picture, it is showing that there are so many bullet points, the maximum points where the damage happened. So keeping on mind that we should be cost effective, as well as the plane shouldn't be that much weight. So I think the extra armor should be reinforced in the maximum, in the area where the maximum bullets hit it. So it should be in the wings as well as in the tailor part of the plane, which is called the stabilizer part. So I think the wings as well as the tailor part of the plane should be reinforced with the extra armor.
Thank you for your answer, Mahfouz. So as of now, do we have any results in Desmos? What are the students thinking?
We are just starting to get responses in Desmos, so maybe we should wait a few more seconds before people have enough responses. But it's interesting to see the pattern in which people are putting answers. So, for example, there are different clusters on the images of the plane. Some have lots of red dots and some have no red dots. So I see that people are marking their areas based on the clusters. So it's interesting. Maybe we should wait a few more seconds for the clusters to build up and then see where kind of the consensus goes.
Definitely. And are there any comments till now?
There are no comments on YouTube yet. So people are probably still engaged with Desmos.
Yeah, it's actually interesting that, you know, there can be so many different perspectives about this. What Mahfouz said that also makes sense. What do you think, Kaustubh?
Yes, I think based on what people have marked in Desmos so far, the clusters where we have lots of red dots that represent a lot of bullet holes, I think that's where most people are providing their armor. So they want to reinforce the areas where there have been a lot of bullet damage.
That's really interesting. Yes. So let's see what the experts in the British Army were thinking. So the British Army were thinking just like what you all said and responded. So they wanted to reinforce the areas with maximum damage, like let's say the wings of the plane. So still what they did is they consulted a statistics group, a statistical research group in USA. And in that group, there was a statistician named Dr. Abraham Wald. He pointed out that the bullet holes represent areas where the plane could take damage and still return home. Here, the parts which have been marked as green. But the parts which don't have bullet holes are the parts where, if hit, the plane wouldn't survive, marked here with the red arrow. So probably those planes that crashed in the enemy territory had bullet holes in these areas. So we have a bias in our data because we are making decisions not on all the planes that went into their missions, but on a subset of the planes which actually returned safely. We don't have information on the planes that, which went out and crashed. So we are trying to save those planes which have crashed, but instead we are trying to make our decision on the opposite subset. So the argument here was that there is a hidden factor which we are ignoring if you are just blindly looking at the pattern of the bullets. So the hidden factor here is the survival status of the planes. And it actually splits our total set into two categories, the groups which survived and the groups which didn't. So this is one of the examples that in statistics, we often have counterintuitive results given the data. And often the data has a hidden factor which we need to look at. So when we are making any decision, we must always think about what hidden factor our data has. Another such example is Simpson's paradox. In our previous example, the bias that we encountered was an unconscious bias. We were not really aware of the bias that we were making. But often we might see, especially in today's world, that there are people who intentionally want to use biased data. So this is a very nice cartoon which illustrates this, that this is the head of the business, and he is hiring associates. And while hiring associates, he is saying that there are lies, then there are damn lies, and then there are statistics. And we are looking for someone who can make all the three work for our company. So that is why we are having this conversation, this session, so that we can make you aware of this kind of issues. So as a mock example, let's imagine we are looking into a medicine which is being developed by, let's say, a pharma company, and they want to treat people who are hospitalized with severe COVID. They want to see if the medicine can cut down death rates in such hospitalized people. So the standard procedure to accomplish this is doing a clinical trial. So how are they doing a clinical trial? They are following this particular procedure. They will split the hospitalized patients into two groups. One group will receive the medicine and the other group won't. And then they can compare the survival rate of these two groups and see if the people who got the medicine have a better survival rate or a lower death rate. And based on that, they can decide whether the medicine is actually working or not. So let's imagine that the company actually did this trial and they got some data. We all know, we have actually seen that the COVID survival rates are actually different in male and female patients. So let's assume that researcher A looked at only female patients in the hospital and got some results. The data looks like this. So there are 100 women who didn't get the medicine, and 5 of them died. And there are 300 women who got the medicine, and 18 of them died. So Mahfouz, what do you think is the death rate of female patients who didn't get the medicine?
Mahfouz, you are muted.
Sorry. So total number of female who got the medicine is 300, and out of them died is 18. So it should be 18 by 300, which is 6%.
And what about the people who didn't get the medicine?
And didn't go medicine is out of 100. It is number of people, female died 5. So 5 out of 100, it is 5%. So yeah.
Yeah, that's absolutely correct. So now that we have seen the death rate, Mahfouz, what do you conclude by looking at this data? Is the medicine working?
So clearly it is showing that still the female who got the medicine is getting a higher death rate. So I think the medicine is not working good.
Yes, that's unfortunate, isn't it?
Mm-hmm.
Let's see what has happened in the other part. So in this case, researcher B in the same pharma company, he was working on the male patients, and he also got a similar set of results. This is here in the table. So here we can see that 300 males have got the medicine and 30 of them died. So Mahfouz, what is the death rate among them?
So for no medicine, it will be 30 divided by 300. It will be 10%. And the people who got medicine, it is and died 12 by 100, that is 12%. And
perfect.
Yeah.
Perfect. So what can we say on the death rate in males?
Oh, same conclusion. That is, the people are getting medicine as well as getting higher death rate.
Yes, definitely right.
Surprising.
But we can also see something else, that the death rate in males is just the double the death rate in females. For the females, it was 5 to 6%,
Yeah.
and here it
Yes.
is 10 to 12%. But
Mhm.
yes, as you said, the trend is same. People who are getting the medicine, they are having marginally higher death rates. So the medicine must not be clearly working, right?
Okay. Right.
So yeah, what we observed is the medicine wasn't clearly working. So what we observed, researcher A and researcher B also observed, and they reported this observation to their chief researcher. Now, the chief researcher wanted to see the aggregate results before he reports the data to the bosses. But the thing is, the bosses would really want to see some data that supports the medicine, because they have invested a lot of money and time working on this project.
Yeah.
So when the chief researcher wanted to look at the aggregate results, the combined number of all the patients looked something like this. So there were 5 deaths in women, 30 deaths in men in the group which didn't receive the medicine. So in total, there were 35 deaths among people who haven't received the medicine. So also in total, there were 400 people who didn't get the medicine. And actually, the same number of people got the medicine as well in the other group, 400 people. So for people who didn't get the medicine, there were 35 deaths out of 400. So what is the death rate here?
So it is 35 divided 400. It will be nearly 8.8%. Yeah.
That's correct. And also we see that out of 400 people who received the medicine, 30 have died. What should be the death rate here?
7.5% nearly. Yeah, 7.5%.
Yes, that's correct. So now I ask you,
Hmm.
let's say you have forgotten about the previous table and you have seen this table for the first time. So what would you conclude if you just looked at this table?
Oh, it is quite surprising. Now the medicine is working.
Yes,
So,
that is
yes.
indeed quite surprising.
Yes, death rate is quite lower.
So it seems like a paradox, right? That in each of the individual groups, the medicine didn't seem to work. But when you combine the data and you look at all the patients, the medicine seems to do better. This is what known as the Simpson's paradox. He was one of the first statisticians who actually pointed it out. So what do you think about these results? If these are counterintuitive to you all as well, and you can let us know what your thoughts are, and what do you think might be the reason which is causing these counterintuitive observations to come up. And also you can tell us what we can do to fix this problem. So you can let us know of your thoughts in the chats. So while we wait for people's comments to come in, maybe we can discuss with Mahfouz what he thinks about this strange observation.
Yeah, the results and the tables are showing quite different results. When we think separately for male and female, and the medicine was not working, and while we combine the results, now the medicine is working. So there should have some hidden factor who is working under this scenario. So I think in the first two table for male and female, the number of people who got the medicine for the female is 300, and while for the male person is only 100. So when we just aggregate these two data sets, so the total number of for male and female, so there is no male and female separately. We are getting the aggregate sample or aggregate responses, where the number of medicine as well as number of not get medicine is same, that is 400. So now here the response or sample responses are getting same, while in the previous two table the number of allocation were quite different. As I said, the number of medicine, the people who got the medicine was 300 for female, while it is only 100 for male. So I think this uneven or unequal allocations might be working as a factor behind of this.
That's quite interesting. And as you said, hidden factors, these hidden factors seems to come up everywhere. In the previous example also, we encountered hidden factors.
Right.
So let's see if the students also think the same or not. So Kaustubh, have we seen any responses yet?
No, I'm saying that there might be some difficulty in writing in the YouTube chat for this session. So we might have to proceed without people being able to respond by chat.
That's all right. That's all right. So let's move on then. Yes, so the problem is if the chief statistician decided to only report the aggregate data, the people who are looking at the data wouldn't really know that they are different groups with different birth rates, and actually the death rates are worse in this group. So Simpson, what he did was he pointed out a few issues with this. So first, if we look at the aggregate data, the cohort is not actually homogeneous. There are two distinct groups by gender. And again, as you have pointed out, Mahfouz, this is the hidden factor in this case. Gender is the hidden factor, by which we should really split the data as we could have done in the previous case. The second thing, as you have pointed out again, that the females have a lower mortality than males. It's about half. So there is a difference between these two groups as well. And the third thing, which you also pointed out, is there is an unequal allocation. Most of the people who got the medicine are females, and majority of the people who didn't get the medicine are the males. So in aggregate, when you put this data together, fewer people die after taking the medicine because most of them are women who in general have lower mortality rate. So in short, this could be summarized by saying that the less effective treatment is given to the less severe group. And this imbalance makes us think that the treatment does have a less severe effect as well. So that's the explanation for Simpson's paradox, that there must be these distinct groups, and these distinct groups must have different trends in mortality. This is an example we saw with COVID vaccine, and it can happen in several other situations as well. The third paradox that we are going to look at is called the false positive paradox. And we will also illustrate this with another mock example. So now that we have talked about COVID medicines, let's talk about COVID-19 diagnosis. Imagine that we have an RT-PCR test for COVID-19, like the test that we all have been using for the last 2 years. So imagine that the test is pretty good. It has a false positive rate of just 5%, which means that it gives a true negative result 95% of the time. And this is called the specificity of the test. So the test is very specific. It also has a zero false negative rate, which means that if an infected people is tested, it will always diagnose him or her as infected. So that gives us a 100% true positive rate, which means the test is 100% sensitive. So it's a pretty good test, right? But is it, though, fair to assume that the test results can be considered as accurate everywhere around the globe? We ask this question because we can have different scenarios in this case. So let's say we consider two different countries, let's say USA and New Zealand. So USA has an infection rate of 40%. So COVID is really widespread there. And let's say New Zealand has an infection rate of just 2%. So if we have these two countries, do you think the test will perform the same in both places? So here you can just go to the Desmos link and go to the next slide. In that slide, you will find that there is a yes or no button. Please let us know your responses in the Desmos. We can't really, hear your comment in the chat, so it will be Desmos only. But please feel free to let us know whether the test will be accurate in both the countries. And while we are at it, what do you think, Mahfouz? What should be the response?
Well, yeah, this is really, really very, very time related example in the current situations. So COVID diagnostics. So under the given setup that PCR, RT-PCR test will be conducted under the situation or setup that false positive rate is 5% and false negative 0% and true positive under the given setup. So I think whoever the country is, if the infection rate actually, if the varies, if the infection rate varies, doesn't matter. So under the given setup of false positive rate, true negative rate, and true positive rate, so the test result or test accuracy, I think, shouldn't be vary because the setup is same for all countries. So if the infection rate varies, I think the test result for the test, RT-PCR test, I think the result should be accurate everywhere because
So
the
you're
setup is
saying,
same. Yeah.
so you're saying that the biological procedure that is being followed here is
Yeah.
exactly the same in both the countries. So
Yes.
given the procedure is same, so this test should perform equally accurate in both the countries, irrespective of whether there is much COVID or not.
Yes,
That's what
yes.
you're
I
suggesting.
think because testing procedure, the setup for the testing procedure is same. So I think doesn't matter what infection rate of a country have.
Yeah.
So
Our respondents on Desmos seem to agree with Morphos mostly. So most of them are saying that the test will perform equally.
Okay, that's interesting. Let's see what statistics tells us. So let's look at the example of New Zealand. Imagine that the tests are conducted on 1,000 random people. So we have mentioned that the infection rate is 2%. So that means that most of the people are not actually infected. So we have seen from the previous slide that the test is 95% sensitive and 100% specific. So overall, what do you think will be the accuracy of the test in New Zealand if we started testing these 1,000 people? So again, please go over to the next slide in Desmos. There you will get a set of numbers. Pick the number that you think is the most accurate representation of the accuracy of this test. I'll just go back to the previous slide in order to show you the number so that you have a reference while answering. As I was already mentioning, the test is 100% sensitive and it is 95% specific. And New Zealand also has an infection rate of 2%. So while the responses arrive, Mahfouz, what do you think? What should be the exact number of accuracy for the test being conducted in New Zealand?
so please go to the next slide where.
Sure, I will.
Okay, I hear you're given only two digit where 1,000 people, random people in New Zealand, and where there is a given number that is 2% for overall infection rate. So, so based on these two number, I have to say that accuracy of the test, that how the test is performing, like how the accuracy of that test. So I think it's better if you just can tell me or explain me how actually to measure the accuracy of a test, because I'm testing like RT-PCR test. I just have two numbers, 1,000 and 2%. So can you please explain a little bit, explain how can we explain the or measure the number of by which we can say, okay, this is the accuracy of a test.
That's actually a very good question because while we are talking about accuracy, we haven't really defined what accuracy is. And in the previous slide, we have talked about false positive rate, true positive rate, and countless other things like sensitivity, specificity. And if you ask me, what would be the exact one metric to go to measure accuracy, that's a very valid question. Let's see what the students think. Kaustubh, are we seeing responses yet?
Yes, we have started to get responses in Desmos, and then they range all the way from 100% completely accurate to the infection rate. And the responses are kind of spread all the way through. So I think different students have very different opinions of what the accuracy should be. So I guess it's better if you start by explaining what accuracy is.
Okay. So as we were saying that accuracy is a bit nuanced when we are talking about tests, because there are so many different metrics or the ways that we can measure accuracy. As I said, we are looking at sensitivity, specificity, and so many things. So what we are going to do is you have already seen that we statisticians, we love tables. So we are going to put these numbers in a table. We'll crunch the data and we'll see how we can measure accuracy. So as of now, we start with looking at the two numbers that Mahfouz talked about, 2% and 1,000. So the approximate number of infected individuals, that should be 2% of 1,000, that is 20 people. And so the approximate number of healthy individuals should be 1,000 minus 20, that's 980. So as this test has 100% true positive rate, so all the 20 individuals who have been infected are correctly diagnosed. But the test has a 5% false positive rate as well. So among the 980 remaining people who are actually negative, 5% of them will have a false positive result. So that gives us 49 people who have actually received a false positive result. All the remaining 931 individuals are currently diagnosed as COVID negative, which is actually the true negative. So if we put all these numbers in a table, what do we observe? So we will have a table like this. If you look at this table, Mahfouz, what is the total number of people who is going to be tested positive?
For the New Zealand, yeah.
For New Zealand, yeah.
It is 69.
Right. So there's 20 plus 49, 69. Who will
69, yes.
69 people who will test positive in total.
Positive.
Thank you.
In total, right.
So out of them, as you can see, only 20 people are infected. So now we see that we have a problem. So in New Zealand, if we have a COVID positive test results, that will be just 29% accurate, because out of 69 positive results, only 20 are correct. So that's a problem, that if you have a positive test result, you are not really sure that you are actually COVID positive or not. So we should say that in New Zealand, the test was working with a very low level of accuracy. It's really surprising, right?
Right.
So let's move on to USA then. If we consider a similar set of, let's say, 1,000 individuals there, 40% infection rate would mean that 400 of them will be infected. And as the test is 100% true positive, all these 400 individuals will be diagnosed as COVID positive. Among the 600 non-infected ones, the test with its 5% positive false positive rate will diagnose 5% of 600, that is 30 people, to be positive. If we recreate the previous table for USA without even going into the calculations, we will find that among the 430 people who have been tested positive, 400 are actually infected. So in USA, if we go back to the comparison, a positive test result will be 93% accurate, which is almost the same as the test as advertised by the test. But in New Zealand, with such a low infection rate, it is only 29% accurate. So as you have previously pointed out, the biological process of how the test is conducted, everything is same across the two countries, but the test is mostly accurate in USA, but often can be inaccurate in New Zealand. This is what known as the false positive paradox, as we were mentioning in the beginning. So now we ask ourselves, why does this happen? The reason of this is that the chance of a positive test result is determined by two things. Not just the correctness of the test, not just by how good is the test, but also there is a hidden factor that is the characteristic of the population that we are testing on. So in this case, the hidden factor is the infection rate of the underlying population.
Right.
Also, when the test's false positive rate, that is 5%, is more than the infection rate, that is 2%, we will see more false positive than true positives. So that's the thing. That's the reason of the false positive paradox. So when we are comparing different countries or different setups, it is very important to look at these hidden factors and this false positive paradox in order to, not get a biased opinion on anything. Our next topic is correlation and causation. This is also a very important topic in today's world, as we see various posts, data, and charts in social media where people claim to have established relationship between seemingly unrelated events and occurrences. So here we have an interesting graph where someone has plotted the amount of ice cream sales and drowning incidents across the different months of the year. So if you look at the plot, it clearly appears that there is some sort of a strong relationship between ice cream sales and drowning incidents. But what could possibly be the reason for this relationship? So please go over to the next slide in Desmos if you all want to let us know what you think could be the possible reason for this correlation that we observe. So could it be possible that eating ice cream makes you more susceptible to the risk of drowning? Or maybe drowning makes you crave ice cream? Or I don't know, maybe it's just a mere coincidence that we are seeing here. Or maybe there is actually a hidden factor that we are missing somewhere. We all love hidden factors, don't we? So while we wait for the responses, Mahfouz, what do you think could be the reason behind this?
Yeah, it's quite a very interesting example. Ice cream sales and drowning accidents. So yeah, that initially the graph is showing clearly a very strong relationship between these two. So which is based on two set of data set, and initially both of the graphs are raising, and after some point they are gradually going downwards. So there is strong relationship between these two data set, I can say. But yeah, if I say logically by practical, ice cream sales and drowning accidents, say in a beach, if I say, okay, the people who are having more ice cream, then the possibility or probability of drowning accident is higher. So I think this is also quite interesting, not possible in practice. So I think still that both of the data set are quite very related and correlated, but there's some, as you say, there are some hidden factors who are working behind of these two data set. So I think there should have a hidden factor, or the relationship correlation is just happening by chance, or it is a coincidence.
So you're suggesting that you're saying that there is no causal relationship between the two events, but it can either be out of a mere coincidence, or there can be a hidden factor at play here.
Yes, in practice, if you have any kind of two set of data set, whether taken from in any parts, so if you just plot them with the use of correlation, the formula of correlation, so, and if you plot the data, then you'll have eventually will have the graph of these two data sets. So if both of the data set give you the relationship, or any like this data set giving us very closer relationship, but still, yeah, we have to if you think practically, these two variable, the two terms are quite different things. Shouldn't be one shouldn't be hampered by others. So there should have some, there any causality between these two things. So there should have some hidden factors working behind of this too.
Right. So in spite of seeing a strong relationship in the plot, Mahfouz is really cautious before jumping to a conclusion that there is actually an underlying causality
Right.
behind this. So what are the students responding, Kaustubh?
Yes, interestingly, the Desmos students also seem to be agreeing with Mahfouz again. So some have said that there are no connections whatsoever, but some students have indicated the opposite causality, that drowning makes you crave ice cream.
Okay, okay, that's an interesting perspective. So let's see what can be the real explanation behind this. Is one causing the other, or they are just correlated by chance, or maybe there's a hidden factor at play here? Well, if you would have taken a closer look at the plot, you might have seen that both ice cream sales and drowning incidents are going up during a particular time of the year. That is summer. Summer is causing an increase in ice cream consumption. And while summer is also the time when people tend to go swimming and spending time in water the most, and thereby the number of drowning incidents increase as more people go swimming. So since summer is the hidden factor connecting these two seemingly unrelated events, they appear to be correlated. That's the thing. That's the hidden factor at play here.
Right.
So next, while there was a hidden factor at play behind the correlation that we observed in the previous example, not all strange relationships that we come across in real life have actually a hidden factor connecting them. Sometimes, as Mahfouz said, they can be just correlated by chance, like a mere coincidence. Just like here, as you can see, the divorce rates in a town called Maine correlates with per capita consumption of margarine. That's just mere coincidence. There's no hidden factor at play here. Or if you look into the next example, that the per capita cheese consumption correlates with the number of people who died getting tangled in their bed sheets. These are just simple coincidences. There aren't any hidden factor or some layer behind this, which are actually connecting the dots behind the scenes.
Right.
Another mistake that we often tend to do is confusing reverse causality with a two-way causality. We have here a historic example. So during the medieval period, Europeans used to believe that lices were actually beneficial to a person's health. So what they observed is that there would rarely be any lice on sick people. And from that, they inferred that people got sick because the lice left them. But the real explanation to this is lices do not really like an increase of body temperature. So when a person got sick and their body temperature changed, the lice would just simply move on to another host. So here, illness is causing the lice to leave, not the other way around. So why is this distinction between correlation and causation so important? In today's world, it is very easy to come across several data sets through internet. And if you analyze any data, as Mahfouz said, you will often find correlation between two things. But knowing that something causes another thing to occur is a much more important and valuable information. If ice cream consumption really caused drowning, we could have built a model to predict drowning, let's say from ice cream consumption, right? Or maybe we could have just informed the policymakers of the country that if you want to stop people from drowning, you better ban all the seaside ice cream shops and so on. But that wouldn't have been correct, right? The last topic for today is extreme extrapolation, when we predict too far into the future. So let's start with an example. If you yourself go to Wikipedia sometime, you will come across the data of men's season-based 100-meter sprint timings over the last 40 to 50 years. If you just simply plot them in a chart, it will look something like this. So can we see a trend here?
Yes.
Yes, we definitely can. the sprint times have been linearly decreasing over the years. So can we just fit a linear relationship with year and the sprint times here? Yes, again, we definitely can. And the relationship will look something like this. So now, what can we do from this relationship or this fancy model? Can we just use it to predict future outcomes? Well, yes, extrapolation does exactly that. We can go beyond the normal range of the data and we try to predict the future outcome based on what we have already observed. So now that we have learned that, if the sprint times have been decreasing, when can it reach zero? That's a valid question, right? Maybe we can solve the equation that we previously seen and just figure it out. So we just substitute the time with zero and solve the equation. So if we solve that, we can get to the conclusion that the year equals to 3096 if we substitute zero for time in the equation, which is what we observe if we elongate the line and make it touch zero. So as per this deduction, if we try to interpret it literally, we can say that in the year 3096, the top sprinters will end up being Superman. Do you think it's a reasonable forecast? Absolutely not. We have extrapolated too far from the range of our data. Our data was for 40 years, and we have tried to predict what is going to happen 1,000 years from now. That is not a reasonable thing to do. I can show you a real-life example of exactly very similar extrapolation attempt, which was even published by the BBC in 2004. There was a publication by researchers at the Oxford University that women may outsprint men by 2156. Here is the BBC News article. Well, we statisticians cannot really comment on whether women can or cannot outsprint men in the future. Biologists who have a deeper knowledge behind the science of this might be able to shed some light on that. Nonetheless, irrespective of whether women may or may not outsprint men in the future, predicting a timeline so far into the future is just another poor extrapolation attempt, which doesn't ever make sense. So that brings us to the end of our presentation. Thank you for attending. Hope you all enjoyed the session. I hope you will remember these examples of misuse of statistics. I'm sure you all have seen this kind of things over the last few years, as there are many instances where we had some misleading reports around COVID. We also saw some great work definitely being done by the researchers. For example, we did discover the vaccines so fast, right? So definitely, there have always been good works, but there will always be some dubious claims as well. In general, we will always need to balance between the good work and the bad work. And this bad or unethical practices not just come from the companies, but any person who is talking about statistics, be it in our real life or be it in the examples you saw. They can say this, and when you encounter this, you have to analyze it like we did in the previous hour. So thanks for attending, and I look forward to any questions if you have any.
Yes, unfortunately, due to the problem with YouTube chat today, we can't take questions, it seems. So we'll just thank you all for attending, and you can make the same request of be aware of these kind of statistical fallacies and think about the issues that we discussed. And hopefully you'll all be more informed and more aware citizens because of this. Thanks again for attending. Bye.